All right, let's go ahead and take a look at pressure. So the idea with pressure is when we talk about high pressure versus low pressure, we're looking at particles that are hitting the sides of the container. So if we have a fully inflated tire, draw a circle for our tire, versus a flat tire where we have that shape here. We're looking at what's happening on the outside. So the pressure is going to be pushing out on all of these. So we have a lot of pressure. And then if we have a flat tire, we have less. So we can say we have a little bit. So the more we have pushing out, the higher the pressure. If we look at a soda can before we open it, again, we have the pressure that's pushing outwards from the center. And as soon as we open it, we have no pressure. So the pressure is same inside versus outside. So here we can say that if we look at the pressure, it's like two arrows pushing in. Here we have kind of them equal. All right, and then the last one, if we look at a fire hose versus a garden hose, a fire hose has kind of that little nozzle where it's, so we have a lot of pressure going through, versus a garden hose where we have a little bit of pressure. So each of these lines represents a pressure as a push. So we can think of pressure as a push. And this happens in gas or liquid. All right, so if we look at atmospheric pressure, the idea of atmospheric pressure is pretty simple. So if we have people that are on a mountain versus at the floor versus a submarine, so say full of billionaires at the bottom of the ocean, this is going to get crushed because there's a lot of pressure. So if we look at what's actually pushing down on this person, all of the air that's pushing down pushes down with the force of what we call 1 atm. So atmosphere is 1 atm. This is normal pressure. When you're at the top of a mountain, you have less air above you, so we could say here is space. So less air means less pressure. So we get something like 0.088 atmosphere. So here we could say less air above means less pressure. All right. If we have something at the ocean, not only do we have all of the air pushing down here, but we have water, and water is heavier. So if you think about water, water is heavier. So here we'd have something, if this is at the bottom of the ocean, we might have something like 400 atm. So 400 atmosphere, so 400 times the pressure at the surface of the Earth. So this is kind of the difference. So we have higher pressure below the ocean. All right. And then here we have the idea of a barometer. So barometer is this kind of, this weight is going to push down. So we have a column atmospheric pressure pushing down. The mercury is heavy, it's pushing up. So this is going to be balanced. So the idea is when the atmospheric pressure is high, we're going to have this push up, and this is going to push down and move this column up. So we can say that this is high. When the atmospheric pressure is low, the height's going to be low. And this is why we get millimeters of mercury. So the mercury is mg. Or hg. And then if we were to measure these, we would just say that something like this is 0. We would do millimeters of mercury. So we'd say this is 1 millimeter, 2 millimeters. So this lets us kind of see how the scale is made. All right, and then we have our examples here. So our goal for these ones, we want to go from torr to Pascal. So our plan is to go from torr, let's do it this way. We go torr to Pascal. So we're going to start at torr. We're going to look at the questions that we have here. So we have torr, and we want to go to Pascal. Pascal is PA. So Pascal is going to be PA. So our idea is we're going to go from torr to ATM, and then ATM to Pascal. So torr to ATM, ATM to Pascal. So when we set this up, so we're going to use the conversion factors here. So the first one, torr to ATM, 760 torr is 1 ATM. So torr and torr are going to cancel out. We have the next bit. So we're going from torr to ATM. Here we're going to go from ATM to Pascal. So 1 ATM is 101,300 Pascal PA. So to solve for this, we're going to multiply the top and divide by the bottom. So we're going to take our answer, 380, divided by 760 times 101,300. So we're going to get a total of 50,650 Pascal PA. All right, so that's our first one. Okay, number 2, we are starting with ATM, and we want to find kilopascal. Kilopascal is kPa. So we're going to go 2.38 ATM, and then we want to look at our map. So ATM to kPa is going to be one step. We have this conversion factor. So we're going to go to kPa. So this is going to be one step. So 2.38 ATM, we have 1 ATM for every 101.3 kPa. So here we multiply the top, we divide by the bottom. So we should get 2.38 times 101.3 kPa. So we're going to get 241.094 or 09 kPa. All right. So last bit, we're going to find millimeters of mercury and then torr. So we have 748 millimeters of mercury. So millimeter of mercury is our unit. So we have millimeters of mercury here. And what we're trying to figure out is what is the pressure in atmosphere. So 760 millimeters of mercury is 1 atmosphere. So 760 millimeters of mercury. So these would cancel out for 1 ATM. So when we divide this out, 748 divided by 760, we get 0.98 ATM. Okay, for torr, so torr is same as millimeters of mercury. Because we can see that 1 atmosphere is 760, 1 atmosphere is 760. These are the same. So we can say that's 748 millimeters of mercury is equal to 748 torr, because they're the same. All right, and there's our two answers.